Hey, welcome. Today, we are diving deep into the world of professional firefighting system installation. We're going to break down exactly how these incredible, life-saving systems are actually built, from the very first support hanger all the way to the final pressure test. And we'll be doing it all by the book, following the most critical standards in the industry. So, let's get right into it.
So this is really the big question, right? How do you take what's essentially a pile of pipes, pumps, and sprinklers and turn it into this intelligent, automated system that's ready to protect lives at a moment's notice? Well, the answer is all in the process, a super meticulous, step-by-step process that leaves absolutely nothing to chance.
And here's how we're going to tackle it. First, we'll look at the codes that govern everything. Then we'll virtually build the system skeleton. After that, we'll place the first responders, the sprinklers themselves. We'll then peek inside the system's heart, the pump room, and wrap it all up with those all-important final checks. Let's start at the beginning, the code.
Okay, first things first. Before anyone even thinks about lifting a single pipe, you have to know the rulebook. I mean, every single decision, every measurement, every connection we make is spelled out by a very precise set of standards. And they're all designed for one thing: maximum safety and reliability.
So, what are these rules? We're mainly talking about two key players here. First, you've got the Saudi Building Code, or SBC 801. That gives us the local requirements. Then, that works hand in hand with the big one, the NFPA, or National Fire Protection Association standards. We're going to be zeroing in on NFPA13 for sprinklers, 14 for standpipes, and 20 for fire pumps. And you've got to think of these less like suggestions and more like the absolute non-negotiable blueprints for a system that's built to work.
All right, with our codes as our guide, it's time to actually start building. And the very first physical step is putting up the system's skeleton. This is the whole network of hangers and supports that holds all the piping up in the air. You know, the integrity of the entire system really depends on getting this foundational step perfectly right.
And this is where that code stuff becomes really tangible. NFPA 13 tells us the exact maximum distance you can have between hangers, and it all depends on the pipe size. You can see it here. A smaller 1-inch pipe needs support every 3 meters, but a bigger, heavier 4-inch pipe can go up to 4.5 meters. This isn't just a random guess. It's all calculated to handle the incredible weight of water-filled pipes and to prevent sagging that could, lead to a total failure.
The installation itself is super methodical. So once the pipe run is in position, you fit this U-shaped bracket called a clevis hanger around it. That hanger then gets connected to a threaded support rod that's anchored right into the structure above. And check out that last step. If you're in an area with seismic activity, you have to add an angled brace. That's there to stop the pipe from swinging around during an earthquake. Every single one of these connections has to be rock solid.
Now, spacing isn't just about holding the pipes up. It's also about giving every part of the system room to breathe and do its job. For example, a sprinkler head needs a clear zone of 450 millimeters below it. Why? Because if you stack boxes or put up a shelf in that space, it's going to block the water spray pattern, and that could make the sprinkler totally useless. It's the same for pipes needing 50 millimeters from the ceiling. These aren't just empty gaps, they're essential, functional spaces.
So our skeleton is up and it's solid. Now it's time to install the system's first responders, the sprinkler heads. This is where the engineering really starts to show, and where getting the placement just right means everything for stopping a fire in its tracks.
21 square meters. Remember that number. That is the absolute maximum area that one single standard sprinkler head is designed to protect. This number drives the entire layout of the system. It's all about making sure there are absolutely no gaps in coverage where a fire could get a foothold.
And this is brilliant because it shows how the system adapts to the specific risk of a space. In what's called a light hazard area, think of a school or an office, the code lets you space sprinklers up to 4.6 meters apart. But if you move into an ordinary hazard area, like a parking garage with cars and fuel, that spacing has to get tighter, down to 4.3 meters. The principle is simple. The bigger the risk, the closer together the sprinklers need to be.
So, how do you actually install one of these? Well, you start on the branch line pipe, where you install a T-fitting. From that T, a short vertical pipe called a dropper goes down and connects to an elbow. This little assembly is what lets you position the sprinkler head perfectly so it's sitting right at the ceiling level for the best possible water coverage. And of course, every single one of these joints has to be perfectly sealed.
All right, so we've moved from the sprawling network of pipes out in the building to the central command center that powers the whole thing, the pump room. This is truly the heart of the system. It's responsible for delivering all that water at just the right pressure the second it's needed. Inside the pump room, there's a very clear chain of command. First up is the small jockey pump. Its only job is to maintain system pressure, taking care of tiny, slow leaks so the big pumps don't have to kick on all the time. But when a fire actually starts, that's when the main electric pump, the system's workhorse, roars to life. And then, for the absolute worst-case scenario, if the power goes out, the diesel backup pump automatically fires up. It's a 3-layer system designed for pure reliability.
Now, here's a super important rule from NFPA13 that every installer has to know, the 10x diameter rule. It just means that the pipe that feeds water into the pump needs to have a straight run that's at least 10 times as long as the pipe's diameter. Why? Well, if you have elbows or valves too close to the inlet, it creates turbulence in the water. That turbulence can cause something called cavitation, which is basically like little air bubbles forming and collapsing, and it can chew up the inside of the pump. This rule guarantees a smooth, powerful flow of water.
Okay, we're almost there. The system is pretty much built, but these final steps, they are some of the most critical. This is where we sweat the details, joining the last pipes, verifying every single component, and running the big tests that prove the system is truly ready for action. So how do all these pipes get connected? It depends. For most of the system, on pipes that are 8 inches or smaller, we use groove joints. They're fast to install and create a really secure seal. But for the main arteries of the system, those big, high-pressure riser pipes, you need the maximum strength you can get. And for that, only a permanent welded joint will do. It's all about using the right connection for the right job.
Now, with everything assembled, the final walkthrough begins. This is a hands-on, meticulous check of everything. We're talking about checking the alignment between the pump and its motor, verifying all the controller wiring, and confirming something so simple but so critical, making sure every single valve is in the correct open or closed position. One closed valve in the wrong spot can literally disable the entire system. Nothing gets missed here.
And here we are, the final exam, the hydrostatic pressure test. The whole system is filled with water, and then we pressurize it to 1.5 times its normal operating pressure. So, like in this example, a system rated for 115 psi gets cranked all the way up to over 172 psi, and it has to hold that intense pressure for a couple of hours without a single drop leaking from anywhere. This is the ultimate proof that the entire installation is rock solid.
And there you have it. We've built an entire system from the ground up, following a precise, code-driven path where every detail matters. Mastering these fundamentals is the absolute bedrock of modern fire safety. But it also makes you wonder, with technology moving so fast, what's next? What's the next frontier for protecting the buildings where we all live and work? Now that's a pretty exciting question to think about.